Section 1.2, Graphs of Equations in two variables, intercepts and symmetry. All equations that relate two variables, x and y, can be graphed on a coordinate plane. The graph is the picture of all the points x, y, is a picture of all points that have coordinates x, y that satisfy or solve the equation. Right? Basically, all the points x, y that make the equation true. Yeah. So let's ask a couple of questions. Is -2, 7 on the graph of x squared plus 3 equals y? Well, if -2, 7 is on the graph of the equation x squared plus 3 equals y, then it satisfies this equation, or makes it true. So we're going to test. We're going to take the x coordinate, plug it in for x. We get -2 squared, add 3 to it, and we're asking the question, does that give us 7? Well, -2 squared is 4 plus 3, and 4 plus 3 is equal to 7. So the answer here is yes. Now let's ask another question. Is 1, 4 a solution to x squared plus 3 equals 7? Yeah. Well, if we look at our definition of graph above, it says it's a picture of all points that satisfy or solve the equation. So, is 1, 4 a solution? Well, let's plug it in and see. 1 squared plus 4, does that equal 7? I'm sorry, 1 squared, excuse me, 1 squared plus 3, that's part of the equation, is that equal to 4? And I made a mistake up here. This should not be a 7. This should be a y. Sorry about that. So we're wondering, is 1, 4 a solution to x squared plus 3 equals y? Well, when x is 1 and y is 4, do we get a true statement? Well, 1 squared is 1 plus 3 is 4. So indeed we do. So the answer to both of these questions is yes. Notice, basically it's the same question. To ask if a point is on a graph, or to ask if a point is a solution to an equation, it's asking the same thing. Let's plug that point in and see if it satisfies the equation. So that means that the set of all the solutions of an equation, the set of all solutions to an equation in two variables give us the graph. Give us the graph of the equation. Now we're going to graph our equation, x squared plus 3 equals y. The first thing we might do if we're asked to graph any equation is maybe look for intercepts. You're probably familiar with what a y-intercept is. That's where the graph crosses the y-axis, so the x-coordinate would be 0. And you probably also are familiar with the x-intercept. That's where y is equal to 0 and the graph crosses the x-axis. So let's find the y-intercept. First, let's plug 0 in for x. In our equation, we get 0 squared plus 3 equals y. 0 squared is 0, plus 3 is still just 3. That is equal to y. So our y-intercept has x-coordinate 0 and y-coordinate 3. So it's 0, 3. For the x-intercept, we're going to plug 0 in for y. So x squared plus 3 equals 0. And then we're going to try to find the x-coordinate that goes with the y-coordinate 0. If I'm going to solve for x, I need to subtract 3 from both sides. I get x squared is equal to negative 3. But there, I have to stop. If I look at this equation, there is no value of x that once I square it gives me a negative. So what this means then is that there is no x-intercept. No solution to this equation where y is equal to 0 means no x-intercept. So that means that our graph is not going to cross the x-axis. It does cross the y, it does not cross the x. Alright, so now we've found a couple of points already. We know that the points -2, 7, 1, 4, and 0, 3 are on our graph. Let's find a couple of more points using a table of values. Actually, I'm going to do it over here. Let's plug in a 2. If I plug a 2 in for x, I'm going to get 2 squared plus 3. 2 squared is 4, plus 3 is 7, so I end up with the point 2, 7. I'm also going to plug in the point, the x-coordinate, negative 1. Negative 1 squared plus 3, well that's 1 plus 3 gives me 4. I could plug any x values in that I wanted to. Now let's notice something. I already know that the points -2, 7, 1, 4, and 0, 3 are on the graph, are points that are going to be on the graph. Now I also know that 2, 7 and -1, 4. Notice there's a similarity between -2, 7 and 2, 7, right? And a similarity between 1, 4 and -1, 4. When we take a look at our graph, we're going to talk a little bit more about that similarity. Let's go ahead and plot our points so we can get a good picture of our graph. Here's the point 0, 3, the point 1, 4, the point -2, 7, and we also have the point -1, 4, and 2, 7. Our graph looks like a parabola, and we shouldn't be surprised, being that the equation was x squared plus 3 equals y. Any equation of degree 2 is going to look like a parabola. Okay. Now let's take a notice. Let's notice something. Yeah? Notice that the graph of x squared plus 3 equals y is a mirror image across the y-axis. The same points, the points that are on one side of the y, have a point that's like a mirror image on the other side of the y-axis. If we think of the y-axis as a mirror, right? 2, 7 would look and see negative 2, 7. 1, 4 would look at negative 1, 4. And of course 0, 3 would see itself. Okay? This idea in math is called symmetry. Yeah? In general, there are 3 types of symmetry that graphs can have. Okay? 3 types. It is important to note that not every graph has symmetry, yeah, but lots of them do. Our 3 types are called symmetry with respect to, the first one is the x-axis. The second one is with respect to the y-axis. And the third one is with respect to the origin. I'm just going to draw a couple of rough graphs here to kind of show what I mean about the x-axis. You could have a graph that looks like that, or maybe something that is, you know, like that. A mirror image across the x-axis. Mirror images across the y-axis. A parabola like we just saw. Or perhaps something else, you know, just a little bit more interesting. And around the origin, something like this. Symmetry, let me fix that. Symmetry with respect to the origin sometimes is called rotational symmetry. So the idea is if you took a piece and rotated it all the way around the all the way around, let's see, 180 degrees, the piece that you rotate looks like it would become the other piece in an opposite quadrant. Okay. Let's talk about each one of these types of symmetry separately. Alright, so number 1, x-axis symmetry. Yeah. So I'm going to draw another picture of some x-axis symmetry. And I want to notice something. If I have points that are kind of symmetric to each other, and this is x, yeah, and this would be y, the point on the top has coordinates x, y, and the points on the bottom will have coordinates x, still at the same x, but instead of a y, the coordinates will be the opposite of y. Okay? Every type of symmetry has a test for it. Okay? A test that you do with the equation. To test an equation for symmetry with respect to the x-axis, you replace y with the negative y, and then look to see if the equation changes. No change. If you have no change, then that means you have symmetry with respect to the x-axis. As far as y's, why is that true? Why is that true? Right? Well, remember that a graph of an equation is the set of all points that are solutions to the equation. So basically the idea is that if x comma y is a solution to the equation and x minus y is a solution to the equation, they both satisfy that equation, right? So there should be no change in that equation if you're plugging in x comma y or x comma minus y. You should get the same thing. Okay? All right. The second type of symmetry